So, hi everyone. To recap Monday and Tuesday, we've figured out that creating threads is very bad for performance and for memory, and for that .NET provides us thread pool abstraction, which contains a list of pre-created threads for us that we can reuse. We also figured out that task is an abstraction around logical work. It may use a number of threads, or it may not use a number of threads. For example, task delay doesn't use any threads at all. We also saw how we can chain tasks, like we can add some continuation for a task, so when it completes, this delegate will be run. Which is pretty much the same how async await works. We looked at task completion source, the way to create new tasks. So task completion source has a task property, which you can await or do anything with it, and set result method, which you can call from any other thread or any other place of code, and it will set the status of the task into the completed state. And we saw the task yield method, which creates a new task that is not completed yet, but it will complete as soon as it is scheduled to run on the thread pool. So it's a way to force the rest of the method to be executed by background thread, and not the same thread that is calling this method. So today it's all about async await. Async await, basically it allows us to chain tasks in a very convenient manner without callback hell, so that we can have non-blocking code and we can have none of our threads being blocked by anything, to create responsive and performance scalable applications. This is an example of sync method and async method. So, for example, we want to create a method that returns a task that has already been completed and contains some result. For that, we can use task from result method, where we return some result. Let's run this example. So on this line, we are expecting this method to return us a task, and we are saving it to this variable. So if we go inside it, we can see that we are still in the first main thread. We are going here. We are creating a new task from this result. We are returning it to this variable. Here it is set run to completion already, and it will have a result even there now. If we go into our second method, which is absolutely the same, except it is marked with this keyword async, and instead of returning a task instance, it just returns the result for us. The thing is that until that result is returned, this method behaves absolutely the same as this method. It doesn't defer execution of this method or on a background thread, like, for example, async methods in JavaScript work. In fact, this method is completely synchronous for now. So our code, the consumer code, it doesn't make distinction whether the method is marked with async keyword or not. From our point of view, these two methods are absolutely the same. We can see that its signature just returns task for us. From this place, we do not even know whether the implementer of this method has marked this method with async or not. So based on this, the compiler needs to make sure that this method actually returns the task instance, because this code expects us as a task instance to be written into this variable. So in order to do that, this method, if we go inside it, you'll see that we first came here. We didn't come here yet because we went inside this method, and this method needs to return us a task into this variable. Obviously, we are executing all synchronous code that is written in this method on the first main thread still, because we asynchronously went inside this method. And only on the line where we are returning result, some magic happens. Compiler sees that the method is marked with async keyword and it returns task. So it creates a task for us. Compiler behind the scenes, it creates a task similar to task from result. So basically you can think of it as if compiler uses task from result and just wraps it around this value. So here on this line, the task will be returned, and you can see here that we have a task that ran to completion, and its result is Ivan there now. Here we can wait for both tasks, which will happen instantly because they already completed, and will write the results to console. Now let's see another example. Let's imagine we have a task that is not completed yet, some task that will do something. For example, we have a synchronous method that returns task without async keyword. It needs to construct a task, so inside it creates a new task using task delay, which doesn't use any background threads, so it will just complete in 5 seconds. But we are attaching continuation to it, which returns string. So after these 5 seconds will pass, we are calling this delegate and returning this value as a result of the task. What will happen if we debug it? We go inside this method, obviously. We are creating this new task that will finish execution in 5 seconds, and after those 5 seconds, it will write this to console. And this is this task. It's waiting for activation, so it will be scheduled on the thread pool. Then thread pool will run it, will wait for 5 seconds, like not thread pool, but just the timer will wait for 5 seconds, and then continuation will be scheduled to be run on some free thread of thread pool, and the thing will be printed to well, no, it won't be printed to console. It will just set the result of this task into our text, because we are returning it as a result of the task. Well, second example does absolutely the same, only it's async. Here we also have some synchronous part of the method. So if we go inside that method here right now, we are still on the main thread, as you can see on the first one, and we are executing this completely synchronously. However, as soon as we reach the first await, compiler does its magic. It sees that we reached an await. First thing, it checks if the task that is present after await is already completed or not. If this task is already completed, then await doesn't do any magic at all. It just skips completely awaiting it because it's already completed. And it will continue executing the rest of the method completely synchronously, still on the main thread. This is important to remember for later. However, here we have not completed task. We are creating a new task that will be completed in 5 seconds. So compiler sees that we reached an await, and what it does, it returns us this task, returns back here into this variable. However, it not just returns this task, it returns this task dot continue with the rest of the method, something like this. Not exactly, this is not the exact implementation, but you can think of it this way. So whenever any await inside this method is reached, the first await, the task that is returned from this method is basically the task that is coming after await, and with attached continuation of the rest of the method. So absolutely the same like in the method above. So as you can see, I have a breakpoint here, but if I click F10, we came here because this task was returned to us, and this has not been run yet. After 5 seconds have passed, they already passed, by the way, so I can just click continue. This continuation will be scheduled to run on some free thread of thread pool, and actually this is what just happened. So we can see that 15th thread is actually executing this line for us. Coming to the next example, exceptions. So what happens with exceptions? Let's say we have a method that returns us the task, and we want this task to throw an exception. We can write this method like this. However, this is not exactly correct implementation because, as you remember, this method is just a synchronous method that needs to return a task. So if we go inside it, it throws an exception, the method itself. So this part throws an exception, and the task is not even created and not assigned to this variable. So whenever you need to create a task that will either complete, or in case of exception, it will still return you a task, but it will throw, like it will have a fault task with exception, you always need to do this. Return task from exception. Or in case of your code, if you have just some code that can throw an exception, you can always write this try and then catch and return task from exception. So whenever you have some methods that can throw exceptions, and it is not marked with async keyword, you're just constructing and returning a task from it. Consider using that construction, because if you do not use it and some of your code throws an exception, then it will be thrown when you call this method, not when you await this task later. Second example is our async method. As you can see here, this is completely valid case, because same as with the result and same as with encountering the first exception, this method, when it reaches exception, the compiler will see that the method is marked with async keyword, so it will wrap this exception in task from exception for us automatically. So we do not need to do anything. We can see that this method didn't throw exception actually, and we have a task in a faulted state. If you throw operation cancelled exception from within your task using cancellation token throw of cancellation requested, then async methods will also wrap it around the task from cancelled, and task will be cancelled in a cancelled state. So these are four magic things that are happening for us using async keyword. Wrapping around a synchronous result, chaining tasks from the first await, attaching the rest of the method here, wrapping around exception, and wrapping around cancellation. However, there is one thing to know about it. In order for compiler to do that kind of magic, it creates state machines. It's a separate kind of class that has different states that can switch. So it's another class that needs to be allocated on the heap. It needs to, like in .NET Core, in latest .NET Core, it doesn't really matter so much because there were made a lot of optimizations there, but it's still a bit of more of overhead. So if you can use, I would not suggest that you remove async await from methods where you don't need them, because in latest .NET Core, the difference is very marginal, and when you remove them, you might introduce some bugs unintentionally. But if you care about performance and you have some applications that is very high performant, or you have some hot path that is executed a lot of times, you might want to remove async await if you do not need it. I'll just show you an example. This is a tool to see how our code looks after it has been compiled by the compiler. So it compiles your code into intermediate language, and then it decompiles it back into C# language. So here we have a task that just does nothing. And here is compiled version of it. It's just a method that returns task completed task. Now let's just add async keyword here, nothing else. We'll remove result because async methods do not need to return anything if they do not do anything. And I'll just write here async. This is what is now being generated by the compiler. So completely empty method that doesn't even have any awaits, etc. The only thing it has is async keyword. It creates a new state machine class with different methods that it needs, and initializes its state and starts it, returns us the task from the state machine. So if you have like 100 async methods, one colon another colon another colon another, every async method will generate the structure and it will all pile up. Another note about async is that it doesn't work just with tasks. It works with any awaitable. And just as it happens, task is an awaitable. Awaitable is something that has getAwaiter method. Like previously, I showed an example that we can, instead of call wait, we can call getAwaiter getResult. This is basically what async await does under the hood. So this is an example of custom awaitable. So for example, task is an awaitable, so we can await it. A value task is also an awaitable. We can await it. And here I created completely new class, my custom class, where I created a method getAwaiter, which is also completely custom my class, my awaiter. My awaiter, it's a waiter. It should implement iNotify completion interface and have these two methods and one property. Is completed, on completed to run some continuation when it's completed, and getResult gets its result. Implementing this class in this manner allows us to await it. So if you need some custom awaitables, you can always implement it this way, but that's more of an advanced topic. I, for one, in my practice, never needed custom awaitables. So, and yeah, returning back to the note that I told that the customer of these methods, they don't know whether it has await keyword or not. From their point of view, these both methods just return you a task. So async keyword only matters to the implementer of this method. It's just a way to avoid callback hell with chaining tasks with continue with, and instead write a beautiful code. So based on that, the consumer of these methods needs to know that this method returns tasks. That's why it's a good idea and a good practice. Always name all the methods that return tasks, whether it's async or marked with async or not marked with async, doesn't matter. All the methods that return task, they are postfix with async postfix. So whenever you name a method like this, you just add async so that consumers will know that they can await this method, that it has returned a task object. So now one more note about unblocking the thread, why I'm saying that it's very important. Look, imagine that you have a code in your API that has a lot of async calls, like async controller endpoint, which calls async library, which calls async. No, let's imagine first that we have sync method. So you have a sync method to call the database and get the data from it, or to read data from hard disk drive. Let's go with hard disk drive, for example, because I have a picture for it. So you call synchronous method to read data from hard disk drive. This synchronous method returns you data. So you are blocking the current thread until the data is completely read and returned to you. Contrary to that, if you have async method that reads data from database, from network, or from hard disk drive, from some input-output device, there is actually no thread. There is a great article by Stephen Cleary, there is no thread. Because, like I told in our first meetup, when you run input-output operation, our CPU does not do anything at all. So if you just rewrite your code to use everywhere async awaits, for example, you have await in your API endpoint, which calls await on your repository, which then calls await on some library like Redis or MongoDB or something, which then goes to the database. Thing is that you will not consume any threads of thread pool. How does it work? Imagine we need to read data from hard disk drive. So this is your code. Here you call some method of a managed library, for example, that you installed through NuGet package. That managed library gets a memory location for the data that you need either to write to that memory location if you need to download something, or to read from that memory location if you need to send something to another device. And then this managed library, it calls using invokes. It calls operation system kernel under the hood, which then calls a device driver. So the device driver, it sends a request to the device, and it sends it this memory location that this device can read or write to. This device then, it returns the operation status to the device driver. And device driver returns this back through or operation system kernel back to managed library. Managed library creates an uncompleted task for you that does nothing but is in incomplete state. And this task is returned to your code. That's all. This task does nothing on the background thread. Now, as soon as this device received that command to read or write to that memory location and returned to the device driver the status of the operation, it starts reading this data. So the device driver, it has its own CPU, so it has its own memory and its own processing chip that can work. And it sends data to this memory location of your machine, or it reads it. So it happens completely by another device, not by your machine. After it's done reading or writing, it notifies via interrupt. Here, red arrow is like an interrupt to operation system. It notifies about the completion of the operation. And so then this notification comes to the managed library under the hood. Managed library just transfers the task state from in progress to completed, and your task is completed. Now, if you have been awaiting it, you go further into on the next line of your code, and you have the data there. This is how input-output operations are working. This is why we can schedule 10,000 of them at a time, and unless we hit a network bandwidth limit or something like that, our CPU is not going to be taxed, and no context switching is going to occur because our CPU does nothing. There is no thread. This is why it's very important in all our contemporary work when we create our web API applications that read data from the databases to use async await as much as possible, because it's a way to not block any threads. If you use synchronous operations, you will obviously block the thread that is just going to do nothing, but is going to wait, and nobody will be able to use that thread. it's going to wait until operation is complete if you use synchronous operation. By the way, a bit of advanced topic, but I just recalled it, so I'll talk about it. File, read all text, async operation. Under the hood, it has been synchronous for a very long time. So it didn't matter whether you used read all text or read all text async. Whenever this call to operation system happened, it was always synchronous, and it was blocking at least something in the background. It has been rewritten completely from scratch and became completely asynchronous very, very recently. I think in .NET 6 or maybe even .NET 8. So these are great changes. Now we can use file system operations without blocking any threads as well. Now, one of the most important topics when we work with AsyncAwait, not many people are aware of it, but the lack of knowledge about it can lead to some nasty deadlocks. At least it did in the past. It's not a so big problem currently in .NET Core, but it can still be present in GUI applications or in the old .NET. So let's talk about synchronization context. Synchronization context. One second. Yeah, since we talked about async await already, I'll just get back to the example about cancellation first. One more thing with recent features of .NET 6 and .NET 8, what was added is there is another operation, cancel async on cancellation token source, which doesn't block any threads in case it returns you a task. So it doesn't block any threads in case some operations were registered to be run after cancellation occurred. So this thing, it might not always execute instantly. It might block current thread, and this thing will not block it. So you can await CTS cancel async instead of calling the cancel method. Now about ConfigureAwait. So about synchronization context. So imagine we have this code. Let's just skip main for now. Let's imagine we have some on-button click event in GUI application that where we need to get image from external source, from network or from database or from somewhere. And we want to update UI after we got this image. But issue is that on UI, these events are not tasks. They are void type. So we can't really await here. Well, we can make async void, obviously, but we couldn't do it in the past. So let's, for the sake of this example, imagine that we need to, for some reason, to block this thread. So what we can do, we can run our async method to get our image. For the sake of this example, it's just waiting for 1 second, but let's imagine that it gets an image and it takes 1 second. And we are getting the result from it. Obviously, this is very, very bad because when we click on the button, our whole UI will freeze for 1 second because we are blocking on this operation. But let's imagine it completely suits us. Maybe it doesn't take 1 second, but 1 millisecond. Maybe it's an operation to read file from disk or something like that. And we're getting this file and doing something with it. Let's run this example. So what we can see, we wrote inside on button click and we wrote start with external HTTP call. And that's all. Nothing is happening. We cannot do anything. So what is happening here? Some bug crept into our program. The answer is simple. It's a deadlock. We got a deadlock here. Why we got a deadlock here? Well, because on UI frameworks, there is in .NET there is such concept as synchronization context, and in UI frameworks like Windows Forms or VPF, there is a specific synchronization context set, and all these events, like on button click, etc., they are being run on this custom synchronization context, not on just thread pool basic threads without any synchronization context. I'll tell you what the synchronization context is a bit later, but the general thing is that whenever you have a framework, like a UI framework, and it creates methods for you, like on button click, and you just write code in it, you have no idea who or how is calling these methods because it's a framework. So framework can use any kind of instantiation of tasks. So it can create a task to run this delegate of yours that you wrote on some custom scheduler or with some custom rules. It's completely the same with ASP.NET. So in ASP.NET, we have our endpoints, and our endpoints are being called by HTTP requests that are being processed by the framework itself. So the framework is calling for us our endpoints, and we have no idea how this framework is calling them. In fact, in the old .NET, not .NET Core, .NET, the old .NET also had synchronization context with the same features as in GUI applications. So if you have an old .NET application and you create this kind of code there, you will also get a deadlock, completely the same deadlock. The only place you will not get a deadlock is in new .NET Core or console applications, because they do not have by default synchronization context. But it doesn't mean that they cannot have synchronization context. Maybe some third-party developer or your friend will create a synchronization context in background and will set it somewhere in the middleware, and now all of a sudden you have a synchronization context set. So what is synchronization context? Synchronization context is just a thing that yeah, let me first tell you about why this deadlock is happening. So, or about synchronization context. So synchronization context it's a thing that restricts how the tasks are being scheduled on the thread pool. So for example, in our case, this delegate will be scheduled on the thread pool, but only one thread can run tasks on that synchronization context. This is the main restriction of GUI synchronization context and of all .NET synchronization context. Only one thread at a time can run something. This is an issue because, look, because here we are on the 10th thread. So 10th thread is executing our method on the synchronization context that allows only one thread to execute these things. So when we go inside that method, we reach the first await. And first await, it creates a task for us automatically that is returned here, which did not complete yet. And here's a deadlock happening. Then we, on the 10th thread, we are starting to wait for its result. So the result property will block 10th thread and wait for its result. If I switch back to 10th thread, you'll see that the 10th thread is standing here and waiting until this task is completed. It's completely blocked. It's waiting for this task to complete. However, this task will never be able to complete because .NET returned us this task with continuation of the rest of the method. But this continuation is required to also run on the 10th thread, because this is what synchronization context tries to achieve. It says that all the continuations should also run on the same thread. But so this task has already long completed a long time ago. And this continuation is waiting to be run on some background thread. And not on some background thread, but on 10th thread. But this operation, the result, has blocked 10th thread. So 10th thread will never be complete. This thing is waiting for this thing to complete, but this thing is waiting to be run on the thread that is waiting for this thing to complete. How to avoid such deadlocks? Well, first thing, the first and the most important thing, and the only correct way to fix these deadlocks and never see them again is to never block on async code. Like I told, it's very, very bad. Never call result, never call await. Either use await, and for that, actually, in GUI frameworks, they introduced concept of async void. So you can actually make async void. It's a very bad practice, don't do it, but for events in GUI applications, that's the only way to use await with these operations within events. Or you can change some continuations, etc. But blocking is very bad. But let's imagine for 1 second that we cannot not block here. We need to block here. We need to block here 100%. We need to call that result. How we can resolve this issue? And we know that this continuation is just some side effect. It's, I don't know, transformer data before returning it to us. We do not need this data, these lines, to be run on this synchronization context. We can run it on some other background thread at all. Well, there is this method in .NET that is present on awaitables, like on task, for example, and it configures the task to be an awaitable that this parameter is called continue on captured context. So by default, it's true. So supplying here true is absolutely the same as not calling it at all. However, if we call it and we supply here false, then it will mean that we will not continue on captured context. We'll continue on completely null context without any context at all. So this method will be able now to run on any free threads of thread pool. So if I run it here, we'll see that, yeah, 10th thread is was waiting for our call to complete, and 7th thread has executed. 10th thread executed our operation, and 7th thread was waiting for this operation to complete. However, one thing to note is that this is a very good practice to call ConfigureAwait false on all tasks. On all tasks, the issue is that we cannot call it on just the first task of the method, because if this task is already completed, then await will not await anything. It will just continue executing the rest of the method. So ConfigureAwait in this case does nothing. So if this synchronous method, for example, if this method is already completed, and later we have another await that awaiting something that is not completed yet, but we added ConfigureAwait only on the first await, then we'll still have that nasty deadlock. That's why it's important to add ConfigureAwait false everywhere, on all the tasks, on all the value tasks, on all the awaitable, wherever you have awaitables, and when you're awaiting. This litters the code. It makes our code not beautiful but dirty. It creates a lot of unreadability because we need to add it everywhere, but it's a necessity if we are not sure where our code will be executed. For example, if we are writing code in .NET ASP.NET Core, and we are sure 100% that in our application we will never have any custom synchronization context, then sure, we can skip writing this ConfigureAwait. But if we are developers of a library that we do not know where this library will be used and how, or if we suspect that in future we might use some custom synchronization context, this is a must. I'll just show you a couple examples. For example, this is a poly library, and in this library and in many other libraries, you can just search for ConfigureAwait, and you can see that everywhere where there is an await, there is a ConfigureAwait. 1, 2, 3, 4, 5, 6, just in one file. This is the code for .NET Core itself. And here you can see there is even a separate pull request that just adds a single missed ConfigureAwait in HTTP connection pool. So in case you are not sure if custom ConfigureAwait or custom synchronization context might be used, if you do not add this, it's considered a bug, basically. Now let's dive a bit deeper into synchronization context. This is an example why we need to call it everywhere. So imagine we have do another operation async, right? And it returns as a task that is waiting for 200 milliseconds. But inside this method itself, we are blocking the thread for 300 milliseconds. So by the time we return this task, it's already completed. So this task will be already completed. And so this ConfigureAwait will do nothing, because this await will see that this task is already completed, and it will just continue executing this line on the same thread that was executing this line. So we'll get absolutely the same deadlock like in previous example, because this thing will block the thread, and the continuation will wait for the same thread to be run. And this is, in essence, what is synchronization context and why it was introduced. It's an important feature of the framework. It's not a bug or something. It's a good thing that it exists, not a bad thing. Synchronization context is just an abstraction for different frameworks to schedule some operation that needs to be scheduled in some specific way. So, for example, in GUI applications, only one thread can update GUI elements. So you cannot update a button label, for example, from background thread. If you try to do it, you'll get an exception. And whenever you develop in some component, imagine that you're a developer of a library and you need to implement a component that will work with VPF, with Windows Forms, and with some other framework like, I don't know, Avalonia. So you create a component, but then you need to run some code on some thread that will update some graphical elements. If you do not have synchronization context, for example, like if .NET wouldn't even implement this concept, you would need to develop 3 different components. You would need to write code that dispatches some code using a knowledge about how Windows Forms works, because in Windows Forms, in order to dispatch some, in order to update some elements, you need to use some Windows Forms dispatcher and methods from it to schedule your asynchronous work. In VPF, you need some VPF dispatcher, so you need to use different classes, different methods in order to schedule to run some work on UI thread. However, synchronization context provides us this abstraction. Synchronization context is just a class that has a method post, if very simplified. And this method post, it accepts an action. So instead of calling some specific Windows Forms dispatcher.post action and then you're supplying your action there, you're just using an abstract synchronization context. You're getting current synchronization context using this code, so synchronization context current, and then you're just using a method post on that synchronization context where you pass your action. This is how you can chain some actions to be executed on a background thread and then on to be posted to UI thread. So you can run some actions that will just be executed on the thread pool, and then later when this action is executed, you are posting some action to be executed on UI thread. And it's already framework responsibility to set this synchronization context current. So all .NET, ASP.NET was setting synchronization context current to ASP.NET synchronization context. Windows Forms is setting this property to WinForms synchronization context. VPF is setting it to VPF synchronization context, etc. We can just use it without even knowing what it is. And we can use method post to post something to be executed on UI thread without the knowledge which framework we are going to use. And this is example of, for example, either old ASP.NET framework or on button click method, how we can implement posting some action. So for example, we are getting this image, and then we are chaining this task with continue with. And instead of just updating UI here, because we won't be able to update with continue with any UI, because continue with will run just on random background thread. We are using current synchronization context post to post updating of UI actually on the UI thread. So the specific, I don't know, Windows Forms synchronization context, for example, it will handle this post and it will run your code on the UI thread. This is absolutely the same method like this one, only simplified with async await. Basically, async voids were added to the language only for the case of these events. Never use them in regular code because they will introduce nasty bugs. With async void, you do not have a task, so you cannot inspect its result, and exceptions are also not propagated anywhere, etc. So, but in UI frameworks, you might use async void, and you can just await your image. And then you can update your button here. So you will be able to update your button label equals and result that you get above. Why will you be able to update label here? Continuation is run on some background thread, right? Well, like we just saw in this deadlock example, by default, continuations run on the same synchronization context that was captured when we called await. So when we are calling await, under the hood, await first it checks if the task is completed already, and then it runs this method if it's already completed. But it also gets this synchronization context current, it saves it, then it runs this task, and then it restores the synchronization context and runs this synchronization on this synchronization context. So it uses the method post, and it posts the rest of the method on this synchronization context by default. So if you write here ConfigureAwait false again, then you won't be able to update here any buttons, because then this continuation will be run on a random free thread pool thread. This is why we need to add everywhere ConfigureAwait false, unfortunately, because .NET implemented it in this way that by default is true, just for the sake of GUI applications, I guess, so that people can write this cool code. One more note is that there is a library for the ConfigureAwait. You might want to use it if you are eager to use everywhere ConfigureAwait. It's a weaver, so during compilation time, it will add to all your code before it's compiled into intermediate language. It will add ConfigureAwait false everywhere to all your tasks. So you won't need to add ConfigureAwait everywhere. But as you can see, both Poly library implementers and .NET Core itself, they do not use such libraries. So it's a third-party library, and only if you want to use it yourself. Also, there is one more thing. There is the file editor config in Visual Studio that allows you to configure different errors and warnings for different messages. So it might be a good practice, at least that's what I did for myself, to configure this severity to error. Usually I have it to error, it's for tests now, because in tests I use it a lot. Yeah, this is for all the other code. So this ensures that you cannot even compile your project unless you call ConfigureAwait on all the tasks. So if you have it in your project, it will not compile until you add ConfigureAwait to all the tasks. Synchronization context. One more thing about deadlocks. We discussed task completion source that can be used to create a task that will be completed when you call set result, right? Well, here's an example of how it can also lead to deadlocks. Just fix that compilation error and put a breakpoint here. So here we create two task completion sources, and we create a new task that will just wait for 5 seconds. And yeah, it will wait for 5 seconds. But here, after we created this task, we awaited. So we awaited, which means that after this task is complete, this continuation will be run. Let's put a breakpoint here as well, and here. So here we are waiting for 5 seconds. Let's put breakpoint here as well. Waiting for 5 seconds. Now we waited for 5 seconds. We are setting the result of the first CTS. So this task should complete as soon as we set its result. Let me just put a breakpoint here as well, here, here, and here. All right, we set its result. We got to this continuation, and now we are waiting for the second task to complete. However, after we set this result, nothing else is executed here. Some magic. Well, it's another deadlock. Thing is that by default, task completion source executes its set result. After you call set result, the continuation of the task, all continuations of the task, whether you added them with continue with method or whether you just used await and you have something after await, all these continuations will be run synchronously. So when we called here set result, task completion source saw that this task has this continuation and it started executing it without, so this line is still waiting for this block of code to finish execution. And since we are here started waiting for TCS2 task, but TCS2 task will never be set because we are waiting for all of this to complete. we got another deadlock here. Quick fix for that is when we create task completion source, use task continuation options, run continuations asynchronously. This is a flag that tells us that this task completion source should not wait here until all continuations will be complete. It should schedule all continuations to be run on some background threads and just keep executing the rest, because yeah, this method will be complete pretty much instantly. It will just mark the task as completed. This is one issue that I stumbled upon one time, and I spent like a couple of weeks trying to debug it and understand why it doesn't work. I also used task yield in my code just to fix that behavior, because I didn't understand why it's happening. Yeah, but this is a thing that can lead to some unexpected bugs if you do not know about it. So yeah, maybe somebody has any questions.
I have one question. Thanks for the presentation about the synchronization ConfigureAwait false. As far as I know, in Web API, the HTTP context current is tied to the current request synchronization context. So if we call with ConfigureAwait false, in continuation, we can lose this HTTP context current. So that's why it's I don't think it's a good practice in Web APIs or in these controllers using.
Yeah, if we need to use HTTP context in the continuation, that's a good point. Then we shouldn't call ConfigureAwait false, because you're right. In the old .NET Core, when we had synchronization context, synchronization context is built to current HTTP context. So if you use synchronization context, if you use ConfigureAwait false, you will lose HTTP context. So you should use it only when your operation that you need to run in the continuation should not does not care about anything that might be in the context of that synchronization context. So yeah, it's even a valid code to write synchronization context true, actually. So some people write specifically synchronization context, task ConfigureAwait true, in order to highlight that here we need that synchronization context. And in the new .NET Core, there is no synchronization context anymore. So there is also no need to call ConfigureAwait false if you are sure that all your code will be only executed in the scope of your host.
Thank you.
I also have a small question regarding example that you showed us without with deep nesting of methods that we are calling with async await keywords. In general, if we have such situation when we call one method inside another, and inside this method, for example, we have only return await some other methods and so on, right? So the best solution, do not write like this, do not write async await with such short methods, but only await in the root method? Or how it better?
Yeah, so if you have code like this, let me just if you have code like this, then this this construction, it calls this method returns some value, maybe after waiting something, and this method is just a wrapper around this method, right? It can even have some synchronous code here. As long as it's synchronous, it's going to be the same case. You can always optimize this method to just not use async await at all, because then you are just on this line, you are returning a task string, you're still returning a task string. It will just be created by this method. So it's a small optimization that you might make in order to decrease the creation of this huge state machine. However, yeah.
But do something we should call with await, or just without await but wait.
Yeah, with do something you can call with await, or you can return it just without await if your upper method also returns task string, for example.
Yeah, thank you.
However, there is one caveat here. Whenever you are optimizing methods like this, you might encounter some bugs. I will get more in detail about it in advanced meetup, but if in short, for example, consider this situation. If, I don't know, like random next, something like this. So in this case, if this happens, we are returning task from exception. So later, when you await some tasks that is returned by do something method, you will get this exception. But you will not get this exception when calling this method. If you just remove async await, now you're suddenly getting this exception when you just call this method. So in order to fix this, you would need to write try catch, and in catch you would need to return task from exception. Another thing is with using constructions. So let me just also show this example. Imagine that you have some code like this, and your do something method uses this db variable. Right now it's completely okay, because this operation will completely complete before you exit the scope. But if you remove async await again, then you are returning the task that will use that variable sometime in future, but you are returning this task as soon as you reach this line. And straight after it, you are disposing of this DB. So later when you await the task that is returned by do something, you'll get object disposed exception, because whenever this task will try to use the DB variable, it's already disposed. So you need to consider such cases whenever you do this optimization. This is why I do not suggest to do these optimizations, because they are very marginal and will not probably impact anything. Only do them when you assure that this endpoint, for example, is being called 1,000,000 times per day, or it's a very hot path for you, and do these optimizations careful.
Okay, thank you.
Any more questions?
Thank you for the session. Yeah, there was a picture maybe related to just a general overview with the calls to system level, like to memory. Yeah. Just have a question regarding like the point of managed library here. So it's like a .NET Framework related library, right? And like just from my perspective, the call, it's like a system level, like working. It's rather related to working with the hardware, right? Like input, output operation. And just wondering if, like from my perspective, managed library shouldn't know anything about, like it's rather related to drivers or system to manage callback, kind of callback here. Just
Yeah, well, all of managed libraries in .NET, they are in some way or another, they are using system calls to talk to different devices.
Yeah,
So,
but Arrow just directed the managed library, so that's why I'm asking.
Yeah, I just missed here a step of unmanaged library, I guess. So yeah, managed library, it's calling some unmanaged library. This is basically, I guess I showed it with this pinvoke call, because you can call the pinvokes from some library. So I guess we can consider this managed library block as both a managed library that is calling unmanaged library. So by managed library, I mean something that we are using without knowledge of how it is implemented.
It shouldn't know any like things related to machine memory or something. And it's rather related to system and unmanaged, like drivers and so on. Yeah. Okay.
Anyone else? I didn't manage to talk about everything that I wanted to discuss, because it's already 3:11 and we only had time till 3, I guess. So I'll move some discussion to Friday. So on Friday, we are going to discuss synchronization, concepts between threads, and also communication between threads, as well as thread safe collections. So the ways to manage data between the threads safely. But I guess we'll start with a bit of other topics that I didn't cover today, like value task and async disposable, and also these things that I just showed, like the issues that can be present when you are doing the optimization. But other than that, yeah, if nobody else has any questions, then see you on Friday. Thank you for joining.